So, hello everyone. It's a pleasure to introduce Tomasz Adamowicz. Okay, I changed his name, but now I did it wrong. From Warsaw, who is speaking about isoperimetric inequalities and curvature of level sets for harmonic function on smooth and singular surfaces. Enjoy. So go ahead. The stage is yours.
Many thanks for this nice introduction, and also thank you for inviting me here and giving an opportunity to present some of my results. Let me know if you can see the presentation and if you hear me well. Is everything fine in that terms? Can you hear me?
So I can hear you clearly and see everything.
Okay, okay.
Just go ahead.
Okay. Very good. So my presentation is based on a joint work with Giona Veronelli from University of Milano Bicocca, and also on some other of my papers. And let me begin with the first part about the isoperimetric inequalities for level curves of harmonic functions. Since the subject of isoperimetric inequalities relates to a legend about Dido, described by Virgil in the 1st century before Christ, I would like to start my presentation with sharing with you a painting by William Turner, Dido building Heritage. I suspect that Dido might be somewhere here, applying the isoperimetric inequality. But more in mathematical terms, let us recall what the isoperimetric inequalities are. And for this, let omega be a set in the plane and closed by a curve denoted by a boundary of omega. And by A, we denote the 2 Hausdorff measure of omega, and by L, 1 Hausdorff measure of this curve. Then the isoperimetric inequality asserts that 4 pi A is less or equal than L squared. And the equality holds for a circle. There are a number of approaches to isoperimetric inequalities, and one of them is on Riemannian manifold. So let M be a complete Riemannian manifold. Then there exists constant alpha bigger than 1 and a positive constant I alpha, so that the following inequality holds for any closed smooth submanifold N of M. On the left-hand side, we consider a volume of this manifold, and on the right-hand side, the surface area of the boundary of submanifold N. It's quite interesting that this inequality is equivalent to a Sobolev type inequality for smooth, compactly supported functions on manifold M. So let's now state what is the connection between isoperimetric inequalities and partial differential equations. And for this, let's start with the geometric setup and denote by D0 and D1 2 planar convex domains, which define a convex plane ring or annulus D. Then for a function U on the ring of class C2, we define the length of a level curve of function U simply by the integral over the level curve of function identically 1. With this notation, Longinetti in 1988 proved that if U is a C2 solution on annulus and continues up to the closure of this annulus, and it is a solution to the p-harmonic Dirichlet problem with constant boundary data, then the following inequalities hold. For p equal to 2, so in the harmonic case, we have the convexity of the logarithm of function L, and for p different than 2, we have the following convexity for a power of function L. And what relates these inequalities with the classical notion of isoperimetric inequality, and what justifies calling them isoperimetric inequalities, is that equalities hold if and only if a level curve is a concentric circle. In the same work, Longinetti also considered a harmonic non-homogeneous problem on annulus with constant boundary data. And for this type of problem, he proved the following inequality. And again, equality holds if and only if a level curve is a concentric circle. Next step in the development of such inequalities was made by Alexandrini, who was able to give up the assumption of convexity for components of the annulus and also proved the Longinetti's observations for a class of aharmonic equations in that form. Then Alexandrini's isoperimetric inequality is a following one with parameter alpha depending on the growth of this aharmonic operator A. And the equality here is slightly more complicated because if this is because the equality here occurs for a circular annulus and for a properly chosen p-harmonic function, such function that p is defined in terms of the growth parameter for aharmonic operators. At this stage, let me maybe give slightly wider perspective for this problem and related to the capacitary problem of finding a properly regular function u, for example, Sobolev regular, such that it solves the p-harmonic equation in the given annulus with 0 and 1 data on the inner and outer part of the boundary of the annulus. And then a part of this capacitary problem is to study the properties of such solutions. This problem has been studied in a variety of contexts. For example, for p-harmonic functions in Euclidean setting by John Lewis, and also recently by Fogagnolo, Mazzieri, Pinamonti, as well as in a series of papers by Jie Xiao. In Carnot groups, in a paper by Dragoni, Garofalo, Salani. Moreover, a capacitary problem has been studied for harmonic functions on space n-forms by Ma and Zhang. And to finish this historical picture of isoperimetric inequalities for PDEs, I would like to very briefly state one more result for component functions of p-harmonic mappings. In order to do this, let me very briefly recall what are p-harmonic mappings in the plane. So these are Sobolev mappings from an open set in the plane with values in the plane, which satisfy this system of equations, the p-harmonic system of equations understood in the weak sense. Here, du stands for a Jacobi matrix of a map U, which means that the rows of the matrix are the gradients of component functions of a map. Of course, when p is equal to 2, we retrieve harmonic mappings, but for p different than 2, this system is coupled by the appearance of Jacobi matrix. And if you have never seen this notion before, let me just state that p-harmonic mappings appear in a variety of applications in nonlinear elasticity theory, fluid dynamics, cosmology, and glaciology. So for such mappings, or more precisely for a component function, we can prove the isoperimetric inequality under slightly stronger assumptions comparing to Alexandrini's Longinetti's results. We need to assume that a map is C-free and it's defined on a subdomain of a domain, and then that the gradient is separated from 0. For harmonic functions or p-harmonic functions on annuli, for example, this property is known, as you will see in a moment. But for p-harmonic mappings in general domains, it's not that automatical. Nevertheless, if we consider function L of S, the length of a level curve U1 then we have the following inequalities. Similar to Alexandrini's work, the same for p equal to 2, but for p different from 2, the right-hand side is non-zero, and it depends on the LP norm of the differential. The equalities are attained if the second component function is identically 0 or u1 is equal to u2, and for omega prime a circular annulus. In this case, u1 is a radial p-harmonic function. Of course, whatever I stated for first component function can be as well stated for the second component function. So this is everything about the historical sketch and the state of art, at least for isoperimetric inequalities and PDEs. The key problem for my presentation is to study the isoperimetric inequalities on Riemannian 2 manifolds, first in the smooth setting, and then we'll see if an isoperimetric inequality can be proven for singular surfaces. But let's first set up the stage and denote by M a two-dimensional Riemannian manifold with the Gaussian curvature K, which may vary from a point to point on the surface. By omega 1 and omega 2, we denote the two simply connected domains with boundaries gamma 1 and gamma 2 respectively. And for the sake of simplicity, in the first part of presentation, we will assume that those boundaries gamma 1 and gamma 2 are C1 alpha regular. But in the second part of my talk, you will see that this assumption can be weakened and allow a Jordan curves as well. And so the harmonic Dirichlet problem in annulus that we will be interested in is the following. We will be considering continuous up to the boundary harmonic solutions of the Laplace-Bertrami equation in annulus with constant boundary data. So a problem analogous to the one studied by Alexandrini and Longinetti. Then we use the same notation to denote the length of a level curve, L of t. And the result that we proved with Giona Veronelli is the following. If omega is a C1 alpha topological annulus in Riemannian 2 manifold with a Gaussian curvature on annulus less or equal than 0, then for a solution to the above stated Dirichlet problem, the following inequality holds for all t between t1 and t2. And the equality in the assertion holds if and only if the curvature is identically 0, in which case all the level curves of U are concentric circles in omega, and omega is the proper circular annulus in the plane. So the statement of this inequality is very similar to the harmonic version of Longinetti's result, with the difference that the curvature appears. Let me describe the sketch of the proof. It consists of 3 main steps. The step number 1 is an observation that in our setting there are no critical points in annulus. More precisely, if M is a 2-dimensional Riemannian manifold and U is a harmonic solution to the Dirichlet problem in annulus with constant boundary data, then the gradient is non-zero in omega. Observe that there is no assumption about the sign of curvature or any assumption about the curvature. In fact, it's because the lemma is actually about the dimension than about the curvature. It's the dimension 2 that plays the key role, allowing to show this result with our approach. But before I will say more about it, let me just mention that this lemma is known in many settings. For example, for planar elliptic PDEs, it's due to Hartmann-Wintner, who used harmonic approximation. It's known for p-harmonic functions in Rn, where it is due to John Lewis, who proved it under strong assumption that rings are convex, and he was using the barrier arguments. Also, this lemma is known for harmonic functions on space n-forms, and it's due to Ma and Zhang, who adapted Lewis' argument. In our case, the proof of a lemma is based on the structure of critical points for harmonic functions in dimension 2, and on the knowledge how the level curves look like close to the critical points. This is very, very particular structure known for harmonic functions in the plane, which is the same as for the same structure as for holomorphic functions. And so the approach that we took to prove this lemma is very difficult to be extended to higher dimensions. And in general, the structure of critical points and the structure of level sets beyond the plane is quite complicated. And if you are interested in this type of problems, then I would recommend a series of papers by Enciso and Peralta Salas, and a survey by Magnanini. In step number 2 of the isoperimetric, of the proof of the isoperimetric inequality, we show that since the Gaussian curvature on annulus is non-positive, we have that the logarithm of the magnitude of the gradient is a super solution. And this, combined with the minimum principle and Hopf lemma, allows us to obtain that not only the gradient is non-zero in the annulus, but also on its closure. And in fact, the first observation is a special case of a more general result, which I will state now. If omega is a two-dimensional Riemannian manifold and U is a harmonic function in omega, then the Laplacian of the logarithm of the magnitude of U is equal to the Gaussian curvature at points where the gradient is non-zero. Notice that there is no assumption here that omega must be annulus, just a domain with no critical points. The proof of this lemma relies on Kato inequality, which in dimension 2 becomes the equality, and also on Bochner's identity. And finally, in the last step, by direct computations, we may show that the following inequality holds for the first derivative of the length of a level curve with respect to parameter t, L, and the second derivative of L with respect to t. And it's quite interesting that formulas allowing to compute L prime and LBs can be stated not only in dimension 2, but also in higher dimensions. Since the following lemma holds. If U is a harmonic function with a gradient non-zero in a topological annulus in n-dimensional manifold. So we don't know if beyond dimension 2 it's true that the gradient is not vanishing, and that's why we need to assume it. And U is a solution to the Dirichlet problem with constant boundary data. Then we have two formulas for L prime, the first one and the second one. And moreover, we can show the following inequality for the second derivative of L with respect to t. And if omega is additionally a domain in two-dimensional manifold, then this inequality takes a stronger form of equality. So in dimension 2, on topological annulus, we have the following identity for LBs. So how do we show these equations? First, for L prime, since the gradient is non-zero, this vector nu defines a unit vector normal to the level sets of U. And then by applying a very definition of the derivative, we obtain that L prime is equal to the following limit, which by definition of nu equals to the following equation. And then by applying Stokes' theorem, we arrive at this expression. And by using the co-area formula, we get the first identity. In order to get the second representation formula, we first observe that the following identity holds for all C2 functions. And then since in our case, Laplacian is 0, this term vanishes and we obtain exactly what appears under the integral in the second representation formula. And the derivation for LBs is quite similar. We again start with the definition of the derivative, use a formula for L prime, Stokes' theorem, compute this divergence, apply the Bochner identity, and at this stage we use the n-dimensional Kato inequality, which combines this expression with this type expression and allows us to estimate this long expression by this right-hand side. We again apply the co-area formula and get the inequality in the statement of lemma. So what happens when n is 2? First of all, the Ricci term becomes a square of the gradient times the Gaussian curvature, but then also the Kato inequality becomes equality, which is exactly nullifying the numerator in this expression. So we are left with those two expressions, which again, when applied, the co-area formula give us the equation for LBs in dimension 2. And so by using this equality with these identities and some standard inequalities like Cauchy-Schwarz inequality, we obtain this inequality, which is equivalent to assertion that the logarithm of L second derivative is greater or equal than 0. So this is everything about the proof for the isoperimetric inequality in the smooth setting, but it has a number of peculiar features. One of them is that it actually characterizes surfaces with non-positive curvature. Because if M is an open surface and K, the Gaussian curvature, is non-positive on that surface, then for every topological annulus and solution of the Dirichlet problem with constant boundary data, we have isoperimetric inequality. This is what we proved, but also opposite. If this property of isoperimetric inequality holds for any topological annulus, then this implies that the Gaussian curvature must be non-positive in M. And there is another slightly more quantitative formulation of this isoperimetric inequality, which, however, requires slightly stronger assumptions. If M is a complete non-compact surface with Gaussian curvature satisfying the following inequality with kappa 1 and kappa 2 non-negative, and U is positive harmonic in the whole surface, then the following inequality holds for harmonic functions with satisfying the constant boundary data. And the reason we strengthen assumptions comparing to the previous inequality is that in the proof we use the following estimate, which requires this non-compactness and the positivity of function on the whole surface. And if you are interested in examples of surfaces that satisfy assumptions of this lemma, I refer to my work with Giona. So this is everything about the smooth case. But now we would like to ask a question if we can find a counterpart of this inequality in setting of singular surfaces. So before I will state this result for singular surfaces, I would like to give some motivation why studying the singular surfaces might be interesting. And in order to give this motivation, I will quote Mark Trojanov's paper on Alexandrov surfaces with bounded integral curvature. So a story about Henri Lebesgue says that following a class by Darboux, where the master proved that any developable surface in R3 is a ruled surface, the young Lebesgue threw a crumpled handkerchief on the table and said, "This handkerchief is a developable surface, yet it's not ruled." So Darboux was doing classical differential geometry, and Lebesgue observed that in nature, surfaces are rarely smooth. It turns out that there is a notion of surface that unifies the Darboux approach in terms of the smooth differential geometry and non-smooth geometry of Lebesgue, and this notion is called the Alexandrov surface. There are a number of definitions, highly non-trivial to show that they are equivalent, but I will state in my talk two definitions. So I want to define Alexandrov's surface, also known as a surface of bounded integral curvature, or simply big surface for short. And for this, let SD be a compact topological surface S endowed with a metric D, such that this surface S in metric D is a geodesic metric space. Then the surface S is said to have bounded integral curvature if there exists a sequence of smooth Riemannian metrics Gj, which satisfies the following two conditions. If we consider an integral over S of the Gaussian curvature associated with Gj with respect to the Riemannian area measure, then all such integrals are uniformly bounded. The second condition, the distances induced by metrics Gj converge uniformly to the underlying metric D. By this convergence, I mean that the supremum distance of Dj and D goes to 0 on S. And then the unique weak limit of the sequence of measures Kgj and μj is denoted by d omega and is called the curvature measure. And it turns out to be the radon measure. As already mentioned, there are many definitions of the big surfaces. For example, based on the polyhedral approximations, and this one is due to it goes back to the original Alexandrov approach. And also there is a direct definition of the curvature measure as an outer measure based on the Gauss-Bonnet theorem. All these equivalent definitions are well described in a series of papers by Trojanov and in a survey by Reshetniak. In the end of my talk, I will provide more references to those papers. So, do we have many examples of big surfaces? In fact, quite many. For example, compact polyhedral surfaces are big surfaces, as well as locally cut zero surfaces. Then compact metric surfaces with lower bound curvature in the sense of Alexandrov. In particular, the compact Gromov-Hausdorff limits of surfaces with lower bound Gaussian curvature. And this class of examples is well described in a book by Burago, and Ivanov. Recently, Litchak and Stedler also proved that RCD K2 surfaces are big surfaces. I don't want to step into definition of RCD space, but this acronym stands for Riemannian curvature dimension spaces, and it's a very fruitful approach to studying the generalization of Riemannian geometry in abstract metric spaces. And another example of Alexandrov of big surfaces are the surfaces with conical singularities. This means surfaces which are smooth Riemannian except for a discrete set of singular points where the metric structure is similar to the one of the Euclidean cones. All right, so we are now in a position to state the counterpart of the isoperimetric inequality on singular spaces, singular surfaces. So let SD be a closed surface with bounded integral curvature with non-positive curvature measure omega. And then we consider omega a non-degenerate topological annulus in S with boundary components being the Jordan curves. And then we consider the same Dirichlet problem as in previous results. That is, we take the Laplace-Beltrami operator on S and look for harmonic functions with constant boundary data on components of the boundary of annulus omega. Then there exists a unique continuous up to the boundary solution to this problem, and the length of the level curves is such that a logarithm of L of t is a convex function on the closed interval t1 and t2. So we see that this is a conspicuous generalization of the differential inequality from the smooth case. I would like to discuss a sketch of the proof, but first the general idea. This general idea goes back to another approach to Alexandrov's surfaces, which is due to Reshetniak and Huber, who observed that Alexandrov's surfaces can be seen as conformal deformations of smooth Riemannian surfaces. This means that we can introduce a smooth Riemannian metric H on S, which is equivalent to an underlying metric D. And then the curvature measure is represented as a weak Laplacian of a properly chosen distribution. And hence this approach allows us to combine also some potential theoretic results, and it makes this theory quite interesting. So in order to prove the log of LT convexity, let me first introduce one more definition. So let S be a closed Riemannian surface, and recall that by this we mean a compact surface without boundary. Then we introduce a class VSH, which consists of the L1 functions on S, such that if we take the Laplacian with respect to a metric H, it defines a signed measure, in which case function U is called a potential of measure mu. And if you are interested in more concrete description of this class, then it turns out that the function U belongs to class V if and only if it's a difference of two subharmonic functions. And moreover, this class is contained in a Sobolev class of functions W1P for any P between 1 and 2. So we have a class of functions, and now we introduce the way to modify a metric, which will give us a smooth metric. So for every function V in the just defined class VSH, we define a distance function DHV as an infimum of the following expression, where the infimum is taken over all Lipschitz paths joining points X and Y. And it turns out that this function is indeed a distance on surfaces without cusps. In a moment, I will give a precise definition of no cusp condition, but for us, it's enough to think about it in terms of the geometry, so that there is a surface without sharp peaks. The result due to Reshetniak and Huber states that if S and D is a closed surface with bounded integral curvature without cusps, then we can introduce a smooth Riemannian metric H on this and find a function V in class VSH such that this modified distance agrees with given distance D. And we say that a big surface is without cusps if the curvature measure of any point is less than 2 pi. In particular, the big surfaces with non-positive curvature measure are without cusps. So this is assumption of our isoperimetric inequality in that setting. Also, all smooth surfaces are automatically without cusps. And therefore, if we consider surfaces with the assumption that the Gaussian curvature is non-positive, they are included in the discussion as well. The proof of the log L convexity consists of the following steps. First, we show the uniformization lemma for annuli on big surfaces, which allows us to reduce the discussion from Alexandrov surface to planar annuli with the modified metric. Then we employ the potential theory and observe that the curvature measure is non-positive, implies that the potential of the related signed measure is subharmonic. And finally, the subharmonic function, this potential, can be approximated by a sequence of subharmonic functions which define smooth Riemannian metrics. And with this observation, we may reduce the discussion to the previously proven smooth isoperimetric inequality, and upon appropriate convergence results get the assertion. So let us now say a little bit more about each of those steps. First, the uniformization lemma. It asserts that for a topological annulus on the surface S, this annulus is isometric to the conformally flat annulus in the plane. And by this we mean that we may find a homeomorphism from a flat annulus into the annulus on Alexandrov's surface, and the appropriate function V bar in the class V for the flat annulus and Euclidean distance, so that the following identity holds. And what is more important, that if we pull back the curvature measure via this isometry phi, then this pullback is the following measure. And you will see in a moment why this particular equation is helpful. By using the uniformization lemma, we may show the existence of the unique solution. Because if you use a harmonic function with constant boundary data, then we apply the fact that harmonicity is conformal invariant in dimension 2. And so we obtain the unique harmonic function in the flat annulus with boundary data 0 and minus logarithm of r, which means that this function must be minus logarithm of a distance. And moreover, we may relate the curvature measure to potential theory by the following observation. Since by assumption the curvature measure is non-positive, then so is the pullback. So if so, then the Laplacian of V bar with respect to Euclidean distance is non-negative. And so V bar satisfies in a weak sense the following inequality, which means exactly this type of inequality for any test function psi non-negative. And even more, V bar is not only a super solution in the weak sense, but also a subharmonic function, meaning that V bar is semi-continuous, it's never identically equal to minus infinity, and satisfies the subharmonic mean value property for each ball compactly contained in flat annulus. The latter condition can be as well stated in terms of the comparison principles. And finally, how do we use all these observations to show the convexity of log of L? First, by direct computations, we express the length of a level curve as follows. And then, since V bar is subharmonic, we can find a decreasing sequence Sj of subharmonic functions defined in annulus, which are smooth in a slightly smaller annular domain omega prime, such that this sequence converges pointwisely to a V bar, and also the sequence of subharmonic functions defines a sequence Gj of smooth Riemannian metrics, which are conformally defined as follows. This allows us to observe that the Gaussian curvature of each Gj with respect to each Gj metric is non-positive. So we may now reduce discussion to the previously proven isoperimetric inequality, because again, by applying the conformal invariance in dimension 2, our harmonic function u is harmonic in omega prime, also with respect to all those Riemannian metrics Gj. And recall that Gj all have the Gaussian curvatures non-positive. So this allows us to use the isoperimetric inequality that we proved previously, applied to functions Lj, which are the lengths of level sets for harmonic function u, but with respect to metric Gj. And then we may infer that the logarithm of Lj is a convex function. Finally, exponentials of Sj converges pointwisely to exponent of V bar, and this sequence is also monotone, non-increasing, locally uniformly bounded, which allows us to apply the monotone convergence theorem, which implies that the log of Lj's converge to log of Lt pointwise. And to conclude the proof of the theorem, we notice that the pointwise limit of a sequence of convex function is convex as well. The tiny details that I omitted here is that in the claim of the theorem, we state the convexity also on the closed interval. But if you are interested in this boundary points, I refer to a paper with Giona. All right. So this is everything about the isoperimetric inequalities, but we still remain in the topic of surfaces and level curves. And we would like to discuss the notion of curvature for level curves on Riemannian surfaces. In order to do this, we first recall some notions from the planar setting, namely if U is a C2 function on an open set in the plane, that we may define the curvature of a level curve by the following expression, as long as the gradient is non-zero. And this formula can be found by direct computations for the signed curvature of a planar curve. Also notice that it perfectly makes sense outside of the level curve, as long as the gradient is non-zero, but it has the geometric meaning as a curvature only on the curve. Such expression was studied, for example, by Talenti, who proved that if U is a harmonic function with no critical points in a given domain, then the normalized curvature of a level curve is a harmonic function. And also minus logarithm of the absolute value of this curvature is subharmonic. We can consider this notion of curvature also on Riemannian manifolds, at least on surfaces, by localizing the discussion, introducing local orthonormal frame and computing the covariant derivatives with respect to this frame. What we get is expressions similar in terms of symbols, but of course with slightly different geometric interpretation. And it turns out that we can find an analogs of Talenti's observations for harmonic functions in the plane, also in the setting of Riemannian manifolds, since the following result is true. If omega is a domain in the Riemannian two-manifold with Gaussian curvature K, not necessarily constant. And if U is a harmonic function with no critical points in omega, then the normalized curvature of a level curve satisfies the following equation. And if the Gaussian curvature K is identically 0, then this equation reduces exactly to the Talentis observation. And moreover, we have the following differential inequality for the absolute value of curvature. And again, when the Gaussian curvature capital K is 0, we are back to the Talentis result. Few comments about this theorem. This result generalizes an observation due to Wang-Wang for constant Gaussian curvature, but we allow the non-constant case. And also in dimension 2, there is an associated, in a sense, symmetric notion of the curvature, the so-called curvature of curves of the steepest descent. The curves of steepest descent are curves orthogonal to level curves, and one can also define their curvature, which is called the curvature of curves of the steepest descent. And for such curvature, one can formulate similar partial differential equation and differential inequality as for the curvature of a level curves. For the details, I refer to a work with Giona Veronelli. This theorem has number of corollaries, including some maximum and minimum principles for the curvature, for the normalized curvature. For example, if you use a harmonic on a subdomain omega prime with no critical points, then under assumptions on the Gaussian curvature and the scalar product of gradient K and gradient U, we can show that absolute value of K attains its minimum on the boundary of omega prime. And there are several other similar observations in our work. And so, as promised, I would like to say a few words about the references. The isoperimetric inequalities for p-harmonic mappings can be found in paper number 1. The bulk of my presentation is based on joint work with Giona Veronelli, which is paper number 2. The 2 papers that inspired us to study the isoperimetric inequalities for PDEs are due to Alexandrini and Longinetti. Then the papers about the Alexandrov surfaces that I mentioned are the following. One is due to Reshetniak, and 2 papers by Mark Troyanov. They quite recently appeared on arXiv in the English translation. The original work, one original work is from 1990 and the other one is from 2009. Originally they appeared in French, but in January of this year, the English translation appeared on arXiv. And finally, a paper about the equations satisfied by the curvature of the level curve due to Talenti is number 8. So I think that this is everything I wanted to present, and thank you for your attention.